So the expression d dx means to differentiate with respect to x, meaning that's the variable, our input variable. The most common derivative, d dx of y, is usually written, let's just go ahead and write that as dy dx. So I want you to know, ready, dy dx is the same thing as f prime of x. It's also the same thing as y prime. Okay, now our favorites are going to be this y prime and this f prime of x for a long time, but this guy is going to become very important very soon. Okay, so we will come back to it. And in the freestyle, you saw that I covered the power rule. You saw that I covered the derivative of a constant, and you even saw that I mentioned what happens if there is a multiplier out in front of any piece of your function. You can take that piece and find the derivative and then just put that multiplier back in there and multiply it together. Now he calls it a scalar multiple, and to scale means to move up or to move down, right? It's like part of a dilation. So then we have this thing which he's calling the sum rule, and it looks a lot like the properties of limits, right? It totally looks like the properties of limits, that you could take f of x and you could find its derivative, and then you could take g of x and you could find its derivative, and then you could add them together. So that's really cool and it's very powerful, and like I said, we've already covered that in our freestyle. But just to practice again with that power rule, what if I did give you x to the fourth power? I'd say that my power rule says that you take that power n and you identify it, and then you subtract 1 from it. You use it as the new exponent. So I should have a 4x cubed as an answer there. Well, can I do that if my power is a fraction, right? If I have a rational exponent? The answer is yes. N is going to be negative 2/3, and then I take n and I'm going to subtract 1 from it. And right here, actually write that down. Take 2/3 and subtract 1 from it, as in take away a whole. Now if I have parts, right, I have some thirds, then a whole set of thirds would be 3/3. So notice how I'm converting a 1 into a 3/3. That helps me realize that what I have is a negative 5/3 as a new exponent. And also don't forget to take the derivative of a constant. That will be 0. So I'm going to end up with a negative 2/3 out in front with an x to the negative 5/3 as an answer there. And I'm putting a box around it, okay? Because remember, the derivative of a constant is 0, so that part went away. And the other part was a little bit hard to show my work, so I'm sorry that it's kind of jammed in there. All right, so then what about h of t? That's problem number 3. When I look at that, I am seeing that I have the derivative of 5, and that's going to disappear, right? That's going to just magically disappear because the derivative of 5 is 0. But here, this thing is not in a format that you might recognize. Ready? I'm going to say that this is really negative 1/2, ready, times t being taken to the negative 3 power. Now, hopefully you're feeling good about exponents and your rules for exponents, that if you have a negative exponent, it was developed, that notation was developed simply to represent fractions. And isn't it amazing now, ready, that I can have my multiplier of negative 1/2, and I'm identifying that my exponent is now a negative 3. And if I needed to take away 1 from a negative 3, it would look like this. Negative 3 minus 1 becomes a negative 4. And so there's this thing that you'll notice when you're differentiating is that, and it's just a positive number, well, then the number should get smaller over and over and over again, right? My exponent should get smaller. But if your exponent is negative and you take something away from it, really all you're doing is making it more negative. So this is going to be t, ready? Oh, sorry, my number out in front should be a negative 3. And this is t now to a new exponent, which is negative 4. So it did still get smaller, but it looks different, right? And you're like, I'm not exactly sure that looks like it got smaller. I totally understand your confusion. All right, so here my answer will be 3/2, and you can say t to the negative 4th, or if you want to, you can do 3/2 t to the fourth power. And for a little while, I would like you to practice that. I would like to make sure that you take these problems and you get all the way to back to where there are no more negative exponents in the answer, okay? That way you remind yourself about this negative exponent rule. Now that we've done that, though, I'm running out of room for this next problem. I hope you're doing okay with it. So this, then, notice how before I separated out that -1/2. That was really nice. Right here, I have something that's being taken to the -3 power, and it's got a constant in it. So before I do anything, I'm going to go ahead and do the 2 cubed. You know what I mean? I want to figure out what 2 cubed is, and then I want to deal with that negative exponent. So I'm going to say this is really, ready, 5 over 8, and x is cubed, and this is really 5 over 8 times x to the -3 power. And so my power was a -3, and if I take away 1 from that, what I have is -3 minus 1, which is a -4. And so the derivative of this, all of those things were me just telling you what f of x was. So this is what f of x is. Now I want to do the part where I actually find f prime of x, meaning that derivative, and I'll say that I have a multiplier of 5/8 in front, and I had that exponent, which was a -3, and then I have x, and it has a new exponent, and that exponent is a -4. And so if I try to simplify this, I will end up with -15 over 8 times x to the -4th, which is really the same thing as -15 over 8x to the 4th. So there you go. Okay, now you can take a derivative more than one time, okay? And so the notation on that is that, notice right there, there's 2 primes, there's 3 primes, there's 4. Whoops, there aren't 4 primes, and that's because it's hard to read. So we just put like a tiny little 4 up there. This is unlikely that you will see either of these notations. They make us sad. Very unlikely you would see me use that notation. I really will just write, please take the derivative 4 times. You know what I mean? This is my favorite. If I want you to find multiple derivatives, this one is the most important. There's my dy dx, right? Just take the derivative 1 time. If I put a little 2 up there and I put a little 2 down there, that means take the derivative twice. If I put a little 3 here and here, that's the 3rd derivative. Right there, that's the 4th derivative. So we are practicing that in class, and you should have seen it. So let's see then what happens when I, do something that's like, ooh, really complicated looking, right? That's super complicated looking. In fact, I can barely even imagine what I'm going to get as an answer here. I have to just kind of make sense of the problem first. I'm looking at it and I feel like I have a multiplier of 1/2. F of x is really equal to 1/2 times something. And that something is going to be 1 over the cube root of x being squared. Okay, so the cube root of x being squared, I believe I could rewrite that. I could say this is 1/2 times, ready, 1 over x to the 2/3 power. And remember, I'm using this rule, and you're going to be copying these rules down anyway, so go ahead and copy it down one more time. If you have something to a power here and a root there, you can say this is really the power over the root as an exponent. And then, by the way, it's over 1. I mean, it's under 1. So that means this is really, ready, 1/2 being multiplied by x to the -2/3 power. And I haven't even found the derivative yet, okay? I really wanted to find the derivative, but that just hasn't happened yet. So let me talk about that derivative then. N, I now know that my exponent is really -2/3, and that if I want to find out what n minus 1 is. I will take away 1 from 2/3. And what exactly am I going to take away? I'm going to take away, ready? A 3 over a 3, because that's a whole. And I'm going to W-H-O-L-E, W-H-O-L-E, a whole amount, right? 3 parts out of 3 parts means that I'm taking away a whole number. And so I say I have a negative 5 over a 3 as my exponent. And so my derivative, f prime of x, is going to have that 1/2 out in front. Then it's going to have my power, which was negative 2/3, also out in front. It's going to have my exponent as being a negative 5/3. And wow, that's kind of complicated. But I do notice that, this fraction can be reduced. And so I want to actually go ahead and reduce it. I'm going to say that f prime of x is equal to negative 2 over 6, right? Because I'm multiplying these top two. I got a negative 2. I multiply those bottom two. I get a 6. So this is negative 2/6, which is the same thing as negative 1/3. So my derivative is negative 1/3 x to the negative 5/3. That's my first derivative. Okay, so what about the question? I was asked to plug in 1. And I already knew my answer was going to be super easy because, finding a fractional power like 5/3, it's very difficult unless you're dealing with 1. In which case the answer is 1. 1 to any power is 1. So I'm going to say then, ready? I'm going to find that f prime of 1 is going to be equal to this. It's going to be equal to negative 1/3 with 1 going in there, and I take to a power, and the glory of taking 1 to any power is when you multiply 1 time by 1, you get 1, even a fractional exponent of 1. So what I'm going to end up with, ready, is just a negative 1/3. Ta-da. Okay, because this equals 1. All right, so then what about the second part? Well, I am supposed to take the derivative again. Oh, what? Yeah, no, I definitely want to take this derivative again. And specifically, the derivative that I'm working with is this derivative right here. And I'm having trouble copying and pasting it. I don't know if that's my software or what. So I'm just gonna go ahead and take that new derivative. Ready? The second derivative is going to have a negative 1/3 in front of it, and my exponent was a negative 5/3, and then I'm going to take that exponent, I'm going to subtract 1 from it, so I have negative 5/3 minus 3/3, which is going to give me a negative 8/3, and so this is x now multiplied, the old exponent, see that? This poor computer. Okay, sorry about that. So my old exponent was negative 5/3. That becomes a multiplier out in front. And my new exponent has been reduced by 1. So instead of 5/3, I will now have, ready, 8/3. And ta-da, what will I end up with when I'm done? Well, across the top, I multiply, I get 5. Across the bottom, I multiply, I get 9. And this is x to the negative 8/3. And this one is a little bit more tricky. He says, what happens when you plug in a negative 8 there? And so that, I will say, even I don't feel like doing it right now. Please remember that on the AP exam, you do not need to simplify these. When we're having fun and we're not stressed out, then we totally will simplify some things. But for right now, I'm going to pretend that we had a test, in which case I'm going to throw that negative 8 in there and I'm going to leave it. And I'm just going to put a box around it. And you feel free, again, because we're just having fun, go put it in Desmos and it'll tell you what the answer is. All right? Okay, so that was page 59, and I'd like to move on now. Finding the equation of a tangent line. We talked about it in class. We are dying to figure out, hey, we got the slope. We know what the slope is. That's super easy. How can we find the correct y-intercept for our slopes? So it says, since the derivative of a function gives us a slope formula for tangent lines to the graph of the function, the derivative can be used to find the equations of tangent lines. And it says, hey, note. Okay, you want to take a note here. Sometimes we will want to find a line perpendicular, and that's how he says it. So a normal is a line that is perpendicular. Okay, and so if you have the slope of a tangent, you'll want to flip it and reverse it, right? Opposite reciprocal. Opposite reciprocal will tell you what the slope of the perpendicular line is. And we'll talk more about normals in class. So it says find the equation of the line that's tangent to that graph at that point. And I can do that. This derivative, hopefully you're going to feel like this is a lot easier, right? We've already been doing some practice with this. So we're going to say f prime of x is going to be 4 times 5x to the fourth minus 3 times 2x and plus, ready, that's 0. So I'm just showing my work here so you can see that that exponent went down to an exponent of 4. You can see that that exponent went down to a hidden invisible exponent of 1, and that that constant just straight up disappeared. And so f prime of x is equal to 20x to the fourth minus 6x. Ta-da! And if I want to evaluate that at a point, I'm going to use that x value. Okay, and it was very kind of him, by the way. He did actually give us the y value as well, but sometimes you actually have to go and find it. So you plug it into the original equation, you could find that y value. But today we have an x sub 1 and we have a y sub 1. So we are good. We have everything we need. So ready? My slope is equal to 20 with a 1 being taken to the fourth power minus 6 times a 1. And again, if I was doing a test and I didn't have the time, I could just put a box around that. But here I actually want to get the equation of a line. So I'm going to calculate this. Ready? 20 times 1 to the fourth power is just 20. And 6 times 1 is just 6. And so my slope is just 14. Ta-da! And he writes this little thing where he calls it the m of the tangent. So if it helps you, you could say m of the tangent, right, is that. Okay, so what would then my tangent line, what would it look like? Ready? I'm going to use y minus y sub 1 equals m times x minus x sub 1. And I'm going to fill in that y sub 1 is over there. He told me it's 6. And the slope that I just filled in, it's over there. That's 14. And x minus x sub 1, well, x sub 1 was a 1, and it's right there. I really am going to just leave it like that. Where did all these numbers come from? Ready? X sub 1 is that number right there. And slope of my tangent is this number right here. And this last number, 6, was given to me, so I didn't have to find it. Ta-da, it's right there. And so that is the slope of your equation line. Well, what do I do next? It says find the equation of the normal line. So if my slope was 14, then the equation of the normal will be, right? That's formula up there. It says take -1 and put the slope of the tangent in the denominator. Ta-da! I get -1 over 14. So this is the tangent lines equation. And ready? Here's the normal lines equation. And the normal lines equation will be y minus 6 equals -1 over 14 with an x minus a 1. And that's because he said, specifically he said, pick that same point. So that same point will have in it y being 6, and it will have in it x being 1. And the only thing that changes is this right here, is this normal is a -1 over 15. That's the only thing that changes. Okay? Because he said he wanted it at the same point. All right, there you go. There are a little bit more pieces to this about non-differentiability. Each of these functions has no derivative when x equals 1. Differentiability it's dependent upon continuity. So there's a lack of continuity here. There's a lack of continuity here. This one's just a hole. That one's called a jump discontinuity. This is a vertical asymptote, so there's no continuity right there at that asymptote. Anytime you have a sharp corner or a sharp turn, and specifically notice that the slope was negative here, and then at this corner, very hard moment, there is after it immediately where the slope is positive. because that's a sharp corner, you're not allowed to have a derivative there. So I'm mentioning, by the way, that any absolute value function will have a place where it is not going to have a derivative, and that's going to be at the vertex, wherever that vertex is. This vertex got shifted to 1, but wherever that vertex lives, there's no derivative at that vertex, okay? And then here's another thing. If you have a really fun looking equation where there is what I would call a vertical, this is a vertical slope, just momentarily, and I'm going to zoom in on that as much as for a brief moment. If I was looking at the slope right there, and you do get undefined for the slope, if that's a vertical slope, vertical tangent of any kind, then you can say that there's no derivative there. So all of those things will break or destroy differentiability. And we are moving on now. It says if a function is not continuous, it is not differentiable. Those are those first 3 figures. A function could be continuous but still not be differentiable, and that's the last 2 of those figures above. So here's this, right? All of those, and then here is this, and it is all of those. Okay? So now I'm flippy over to the next side. Find x values where f of x is not differentiable. And I'm going to say the vertex is at 0, 0, and that's where it's not differentiable, because at x equals 0, there is a sharp turn. And technically, I'll mention that our graphical disability here, the thing that makes us, be broken, is that we are trying, we are trying to find a tangent, but there's just an infinite number of tangents. And I can't narrow it down into 1. So that's why I say that I can't find a derivative there. Okay, let's take a look at number 9. And I mean, when I say let's take a look, let's actually take a look. So this part is red and this part is my blue, slightly different blue, but whatever. And I notice right here, then I'm going to say that I have a corner. Okay, it is continuous. Okay, but the corner makes it so that I'm going to say that it's not differentiable. And specifically, I want to kind of mention why, that when I take the derivative of f of x, and for the top part, I would get already a 2x, and for the bottom part, when I take the derivative of 1x, I will get 1. And so if I plug in, if I want to find out f prime, sorry, I meant to use red there, f prime of 0, right, at 0, this is where I'm saying it is not differentiable at x equals 0, and that's going to be my final answer. But here I want to say why. Ready? If I plug in the 2 times that 0 on top, I will get a 0. But on bottom, if I plug in a 0, there's nowhere for the 0 to go. And so my slope is going to be a 1. And so I'm mentioning that the slopes do not match. Okay, now at 0, what if you didn't have Desmos and you couldn't look at the graph? If you plug in a 0 here, you get 0 squared, which is 0. If you plug in a 0 here, you get 0 times 1, which is 0. So you knew that it was continuous if you plugged in 0. And why did I say 0? Because this is where the graph gets funky, right? Where we have the red line changing over to the blue line. And so if you have the graph, you can look at it, you could see the corner. If you're trying to do this algebraically, you look to see if it's continuous. If it is continuous, then you're going to check those slopes. And looking at the slopes and seeing that they don't match, that's what tells you that it's not differentiable there. Okay, so I wanted to actually zoom out to the next question, which is number 10. And again, I have the graph, and here the red, that's still the red, that's this side right here. But now I have a new function down here, which is x squared plus 1. Whoops, it's supposed to be x squared plus 1. My bad, I graphed it wrong. Okay, so anyway, ignore that green line, and let's just transform this into this green line with a plus 1. And when I'm looking at the plus 1, hey, it's not continuous there. So it's not continuous at x equals 1. Therefore, ready? 3 dots laid up like this on top of one another. This means therefore. You're welcome to use it anytime you want. Therefore, f of x is not differentiable at x equals 1. And that will be my answer as well as a reason why. Okay, so those are those two problems. And I will mention again on number 10, if you don't have the graph, you really can, ready? You can really just plug in a 0 here and you know you get 0 squared is 0. You can plug in a 0 here, 0 squared is 0, but then you add 1 to it. This is 1. So that's how you know, ready, that it's not continuous there, that you have two separate heights. And I'm sorry that I graphed that wrong, but I'm not going to go back and re-record it. We are moving along to the final stretch of learning here, and we're going to say then, can we, so check here for those answers. For number 11, it says, can we find x values where f of x is not differentiable? Then I'm just going to set that denominator equal to 0. I'm going to say that x equals 0 is problematic for me, and x minus 1 equals 0 is also problematic for me. Add 1 to both sides, and I'll say that x equals 0 and 1 are not differentiable. And that's because one of them's asymptote and the other one is a whole. So not differentiable. There is a whole at x equals 0 and an asymptote at x equals 1. All right, last one then. Here is my beautiful cube root function. And by the way, if you don't have this guy memorized, it's okay. If I want to talk about f of x equals x cubed, I am really hoping that you do have that one memorized. It looks like this. And so the cube root is like flipped on a line that goes like this. And so this little flip looks like that, and that little flip looks like that. So the purple line is this equation, and that's exactly the graph that he gave us above. You're like, do you recognize it? He already gave us a picture of what that looks like. It's right here. You can label this as some kind of y equals the cube root of x, and it looks like there's some kind of shifting going on. Maybe minus an h is going on here, and maybe some kind of plus k is going on here. There's some shifting to make the vertex move from here. It's moving that way and that way. And so any kind of cube root has at its vertex a place where there's a vertical slope. And so that's why there's no derivative on this one either. Okay. So let me see if I can't get to it. Ta-da! So not differentiable at x equals 0 because of a vertical tangent. Okay, now trying to find that algebraically is very difficult. So that's why we're trying to train you to look at it by knowing what the graph is, okay? Rates of change, we've learned about the average rate of change, which we're calling AROC, which is the slope between 2 points, also known as a secant. Remember that this is also called a secant. And the instantaneous rate of change, we now have so many words for it. It's a slope, but it's a slope at a single point, which means it is the slope of the tangent, which means it is also the derivative. Okay, now we find it by calling it the IROC, which you literally have no reason to ever write that. You can just write, ready, M, or you can write f prime of x at c, at some specific number. Remember, we plugged that in. So here we go for number 13. It says, find the average rate of change from x equals 10 to x equals 30. And that's just going to be an average rate of change. I don't have to actually calculate a derivative here. So that average, it's going to throw you for a while. You're going to be like, which one do we do? Do we find the derivative? No, this is not the one when we find the derivative. And I'm literally just going to write the work down, and I'm not going to talk too much about its calculations. F of 30 equals the same thing as 30 being squared plus 2 times 30, which if you pull out your calculator will end up giving you 27,060. And F of 10 is going to be 10 being, cubed, plus 20 times 10, which if you pull out a calculator will give you 1,020. And so my AROC, my average rate of change, can be written as something minus something over something minus something. And those somethings are going to be 27,060 and 1,020 and a 30 and a 10. And when I'm all said and done using my calculator here, I will get a 1302. Okay, so use a calculator. Okay, the next one though, that's an instantaneous rate of change. I'm wondering what happens at 10 exactly. I'm expecting that I will not get a number nearly as big as 1300, because going from 10 to 30, obviously I went from a height of 1,000 all the way up to a height of 27,000. So there's a big rate of change there. It's changing pretty dramatically. So, but how dramatically is it changing just at 10? Ready? I'm going to find the derivative, and I'm going to say the derivative of x cubed is 3x squared, and the derivative of 2x is going to be 2. And ta-da, all I have to do now is plug in, ready, what happens at 10. And this is actually a lot easier to calculate. I don't even need a calculator for this piece. Ready? 3 times 10 being squared plus 2 is the same thing as 3 times 100 plus 2, which is very easy to find out, is 302. And that is called my instantaneous rate of change, but I want you to call it, ready, the derivative at 10. The derivative of f of x at